Now we look at problem 6, and in the first part we want to use the fundamental theorem of calculus to evaluate the given integral, which is the integrate from 0 to 3 of x times 2 minus x dx. Okay, so firstly we can expand the inner function part to multiply x inside, and then we will have integrate from 0 to 3 of 2x minus x squared of dx. And now we can use the linearity of the integral to write this as integrate from 0 to 7 of 2x dx minus integral from 0 to 3 of x squared of dx. Okay, so next we're going to apply the fundamental theorem of calculus. So first remember the antiderivative of 2x is x squared, and then we're going to write the integral limit. The upper limit is 3, the lower limit is 0, and then minus, remember the antiderivative of x squared is equal to 1/3 of x cubed, and then we write the integral limit, which are 0 and 3. And then we're going to evaluate. So firstly we plug in 3 into x squared, and we will have 3 squared minus 0 squared, and then minus 1/3 of 3 cubed minus 1/3 times 0 cubed. And if we do the algebra, for the first parenthesis we will have 9 minus 0, which is 9, and then minus 1/3 times 3 cubed, that is 9 minus 0, just 9. So finally we have 9 minus 9, we have the integral equal to 0. So this is the first part. We use the fundamental theorem of calculus to evaluate this integral. And then for the second part, we're going to use the midpoint Riemann sum with n equal to 3 to give a approximation to the integral of from 0 to 3 of x times 2 minus x. So basically that is what we did in the first part. And we have the plot of this function x times 2 minus x here, and we're going to use the middle point Riemann sum with n equals 3. That means basically we're going to separate the interval from 0 to 3 into 3 different pieces. So the closed interval from 0 to 3 into 3 different pieces. That is, the first piece is from 0 to 1, and the second piece is from 1 to 2, and the third piece is from 2 to 3. Okay, so numbers here are simple, but sometimes it can be some kind of complicated. So how we can find the how could we find the length of each interval? So remember the formula is b minus a over n, and b here is the right endpoint of your interval, and a here is the left endpoint of your interval, and n is the part you're going to divide this interval into. So basically here we have a, the left endpoint is equal to 0, b, the right endpoint is 3, that is 3 minus 0 divided by n equal to 3. That means the length of each interval is equal to 1. So by the same way we can find these 3 pieces we're going to get are 0 to 1, 1 to 2, and 2 to 3. So 0 to 1, that is first part, 1 to 2, that is second part, and 2 to 3 is the third part. Because we're going to use the midpoint of the Riemann sum, So we're going to find the midpoint of each interval. For the interval from 0 to 1, the middle point is 1/2 or 0.5. And then we're going to draw a rectangle with the height of function value equal to 0.5. Okay, so this is our first rectangle. And for the second part, that is the second interval from 1 to 2, our middle point is 1/2, and then we find its corresponding function value and draw the rectangle, and it is here. Okay, and then for the third part of our interval, which is from 2 to 3, the middle point here is 2.5, and and then because when x greater than 2, the function goes below the x-axis, so this time we're going down to hit the function curve, and this will be our third rectangle. Okay, and then we're going to give an approximation to the integral of given function. That means we're going to use the formula for the area of the rectangle, that is the base times the height, to evaluate the area of each rectangle and then add them together. So for the first rectangle, that is when x goes from 0 to 1, we have the base is equal to 1, and the height is the function value when x equal to 0.5. So we're going to find that function value. That is, remember our function is fx equal to x times 2 minus x. So if we plug in x equal to 0.5, we will have 0.5 times 2 minus 0.5, and then here we have f 0.5 equal to 3/4, or this is equal to 0.75. Okay, and then the area of the first rectangle here will equal to, I will denote the area as S1, equal to the base 1 times the height 0.75. This is equal to 0.75. Okay, this is our first part. And then for the second rectangle, we can do it by the similar way. We firstly find the function value of the middle point, that is f 1.5 equal to 1.5 times 2 minus 1.5. This is equal to 0.75. So the area of the second rectangle is equal to base, which is 1, times the height 0.75 equal to 0.75. So this is the area of the second rectangle. For the third part, we have to be careful because here we have this rectangle below the x-axis, so we have a negative area, and then but the idea is kind of the similar as before. We firstly find the function value when x equals to 2.5, that is 2.5 times 2 minus 2.5. So if we do the algebra, this is negative 1.25, and then the area of the third rectangle is equal to base 1 times the height, but here we have a negative height, that is negative 1.25, and so the area of the third rectangle is equal to negative 1.25. And then to give a approximation of this integral, we need to add the three areas together. That is, we have 0.75 plus 0.75 plus the third negative area, that is negative 1.25, and this is equal to 0.25. Okay, this will be our final result.